Welcome to G Fun Facts Online. Today, we're talking about something you see every single day but probably never think about: concrete. It's the silent, gray backbone of our civilization. Our cities, our bridges, our homes, they're all built from it. But what if that boring block of stone wasn't so boring? What if it was alive? Imagine a building that heals its own cracks, a highway that purifies the air, and a city that actively fights climate change. This isn't science fiction. This is the new reality of concrete, and it's being designed by artificial intelligence. For centuries, the recipe for concrete was simple: cement, water, and aggregates like sand and gravel. But this simplicity hides a huge environmental problem. The production of cement, the key ingredient, is responsible for a staggering 8% of the entire world's carbon dioxide emissions. We've built our modern world on a material that is simultaneously warming our planet. And there's another issue. For all its strength and compression, concrete is weak when you try to pull it apart. It cracks. Under the constant stress of weather, traffic, and time, tiny fissures appear. These cracks are like open wounds, allowing water and chemicals to seep in, corroding the steel rebar inside and weakening the entire structure. This leads to a never-ending, multi-billion-dollar cycle of inspection, maintenance, and repair. The challenge is clear. We need to create a concrete that is not only tougher and more resilient, but also kinder to our planet. And that's where our story begins, with two incredible innovations: self-healing and carbon-absorbing concrete. Let's start with healing. The idea of concrete fixing itself isn't entirely new. There is a natural process called autogenous healing, where unhydrated cement particles and other compounds can react with water to seal very tiny cracks, usually smaller than 0.3 millimeters. But this natural ability is slow and weak, not nearly enough to fix the larger cracks that cause real structural damage. To solve this, scientists are engineering what they call autonomous, self-healing concrete. One of the most promising methods uses microcapsules. Picture tiny, microscopic glass or polymer spheres filled with a healing agent, like an epoxy resin. These tiny spheres are mixed directly into the concrete. Everything is fine until a crack forms. As the crack spreads, it ruptures the capsules in its path, releasing the healing agent. The liquid agent then flows into the fissure, hardens, and essentially glues the crack shut, restoring the concrete's strength. Think of it like the platelets in your blood rushing to form a clot when you get a cut. Some advanced versions even use multi-responsive microcapsules that can release their payload based on triggers like a change in humidity or temperature. But perhaps the most futuristic approach is microbial self-healing. This is where we truly get into the realm of living concrete. Scientists are embedding specific types of bacteria, like Bacillus subtilis or Sporosarcina pasteuriae, into the concrete mix. These bacteria are dormant, often protected inside tiny capsules or absorbed into porous materials. When a crack forms and water inevitably seeps in, it acts as a wake-up call. The bacteria become active, and they begin to feed on nutrients that were also mixed into the concrete. Through a natural metabolic process called biomineralization, these microbes precipitate calcium carbonate, which is essentially limestone. They literally build new stone inside the crack, sealing it from the inside out. This method is not only incredibly effective and environmentally friendly, but it offers the potential for continuous, long-lasting healing as long as the bacteria and their food source are present. Other methods are also being developed, like using crystalline admixtures that react with water to form a non-soluble crystalline structure that grows and fills cracks, or using superabsorbent polymers, or SAPs. These are hydrogels that can absorb and hold huge amounts of water. When a crack forms, the SAPs swell up to physically block the gap and, at the same time, release their stored water to fuel the concrete's own natural healing ability. So we're developing concrete that can heal itself. That takes care of the durability problem. But what about that massive carbon footprint? This brings us to the second revolution, creating concrete that doesn't just produce less CO2, but actually absorbs it from the atmosphere. The goal is to turn our buildings and infrastructure into giant carbon sinks. Ironically, the key to this technology is a process that has traditionally been seen as a weakness in concrete: carbonation. In regular concrete, when CO2 from the air reacts with calcium hydroxide, it can lower the pH and lead to the corrosion of the steel reinforcement. But in these new designs, carbonation is the hero. By incorporating materials with a high affinity for CO2, like magnesium oxide or special proprietary admixtures, we can design a concrete that actively captures atmospheric CO2 and mineralizes it, locking it away permanently within its structure. A pioneering technology in this field comes from Japan, called CO2 Suicom. This innovative concrete replaces a large amount of cement with a special admixture that reacts powerfully with carbon dioxide. The final product is actually carbon negative. That means for every cubic meter produced, it absorbs more CO2 from the atmosphere than was emitted during its entire manufacturing process. Another technology, called Carbonade, uses an automated process to inject CO2 into precast concrete blocks, binding the carbon into the material and making them permanent carbon storage units. Researchers are also getting creative with other materials. At the University of Pennsylvania, a team is using diatomaceous earth, a porous material made from the fossilized remains of tiny aquatic organisms called diatoms. The intricate, sponge-like structure of this material provides a massive surface area for trapping CO2 molecules, while also making the concrete stronger. Now, you might be wondering, how on earth do you figure out the perfect recipe for this? How much bacteria do you add? What's the optimal size for a microcapsule? Which admixture will absorb the most carbon without compromising strength? The number of possible combinations of materials and processes is astronomical. Trying to figure this out with traditional trial-and-error experiments in a lab would take centuries. This is where artificial intelligence becomes the master architect. Machine learning, a subset of AI, is completely changing the game. Scientists feed these AI models massive datasets containing thousands of historical concrete recipes, material properties, and experimental results. The AI sifts through all this data and learns the incredibly complex, non-linear relationships between the ingredients and the final performance of the concrete. With this knowledge, the AI can do incredible things. First, it can predict material properties. Researchers can input a new recipe, and the AI will predict its strength, durability, and even its CO2 uptake before they ever mix a single batch in the lab. This saves an enormous amount of time and resources. Second, it can optimize mix designs. You can tell the AI your goals. For example, I want maximum self-healing ability, and I need to absorb at least 20 kilograms of CO2 per cubic meter, all while maintaining a specific compressive strength. The AI will then run thousands of virtual experiments in seconds to find the absolute best combination of ingredients to meet those exact specifications. It can even discover novel materials, suggesting unconventional recipes that a human researcher might never even think to try. This has led to the rise of what are called autonomous materials, discovery platforms, or